Howdy, this is your friendly neighborhood physics teacher here, and we are doing the FRQ for Unit 5. This is momentum on the AP College Board. So there's two questions. So question 1 states, this question is a long free response question. Show your work for each part of the question. And then it has 2 diagrams. So the first diagram has a ramp, and it has a block up here and a block down here. And it says this is block X, this is block Y, so this is mass of X, and this is mass of Y. And it says this is the initial locations of the blocks. Then it goes to make figure 2, kind of the similar setup, but in this case, block X and block Y, again, MX and MY moving in this direction. And it says it's a 2-block system. And this is after the collision. So this is before, this is after. And it states a solid block X of mass MX may be placed at different locations along a curved ramp. At the bottom of the ramp is a solid block Y of mass MY that is at rest on a horizontal surface. So it's not moving. So velocity Y, initial, is not moving. Figure 1 shows both blocks before block X is released. A group of students must graphically determine the relationship between the released height of block X and the speed at which the 2-block system travels after the blocks collide and stick together. So these stick together. These now become 1. Figure 2 shows both blocks after the collision. Frictional forces between block X and the ramp and between both blocks and horizontal surfaces are considered to be negligible. So there's no friction in this system. AI. Asks for state the basic physics principles, laws, or equations that students could use to graphically determine the relationship between the release height of blocks X and the speed at which the 2-block system travels after the blocks collide and stick together. So, this is like one of those explanation slash write a paragraph, so you can throw some you can throw some equations into the mix. So the students will need to use both conservation of momentum and conservation of energy equations. So you're kind of so you can see that you're needing, because it's saying how does the height compare to that. So you know that for your momentum equation, you're going to have mass X with velocity X before the collision, and your Y is not moving, so you don't have to worry about that. And then after the collision, you have your mx plus your my, and you have your velocity after the collision. We're going to do velocity of them combined. But then you have to do your energy. So you have, before the collision, you have gravitational, but you don't have kinetic, gravitational of x, but y is not doing anything, so it's not moving, and doesn't have any height. It has to equal, so there's no height, but you do have kinetic of x and y. So you're kind of doing like a combination. So you can break that down to mxg y equals 1/2, and this is the combined mass of your Vxy squared. So you're kind of looking at this type of equations. So to basically determine the height, because we're needing height, so what it's asking for height and the speed. And since you have a couple of unknowns in the mix, you would need both of those to compare. So that's kind of, you're looking at, you can write down the equations, you can put it into words, but you're needing to compare the two. A double I is wanting you to derive the equation that relates to the initial release height hx and the block x and the speed vs of the two block system after the collision in terms of mx, my, and fundamental constants as appropriate. So for our double I, we're looking for an equation, and the only things that we can use is h, which that would be just equivalent to our y, and the speed of the two block system. So they're saying Vs, we kind of already called that Vxy, so just kind of showing that they are connected. And then we can use our Mx, Mny, and any fundamental constants would be gravity, theta, mu. Nothing's at an angle, so we don't have to worry about theta, and it says there's no friction, so we don't need to worry about mu. So the only one we can use is gravity. And we need to derive an equation. So we're going to go back to kind of like the equations we already did up here. So we're going to use these equations and figure out how to stick them together so we can compare the two. So we're going to look at our first equation here, and we're going to end up solving for our velocity. So I'm going to rewrite it. So our mx, vx initial equals mx plus my v, and I'm going to go ahead and put an s because that's how they're wanting it. And we want and we're wanting that s by itself. So we're going to divide mx plus my to both sides. So we're saying that our vs equals mx vx naught divided by mx plus my. So that's pretty much as far as we can get as of right now, but we need to figure out how to get this initial speed out of there. We really do. We need to figure out how to get that initial speed out of there. So we're going to use our kinetic energy equation. I'm going to do a different color so we can so I'm going to rewrite it over here. So we have our gravitational, which is just our mass, gravity, and then our height, which we're calling hx. This is mass of our x, equals, and then would be our change in, not change in kinetic, it would just be our kinetic energy. So it'd be 1/2 again, mx, and then our velocity squared. Okay. We're going to try to get velocity by itself. Hopefully you see that you can cancel out your masses. So we're left with gravity hx equals 1/2 v squared. Multiply both sides by 2. So you get 2GHX equals V squared, and then you square root it. And so you get your V equals 2GHX. So I'm going to reread the question real quick, because my answer isn't lining up with the key. And basically what I'm doing right now, I'm looking at the key, and my answer is not lining up with the key. So it's wanting to know, derive the equation that relates the height of block X with the speed of the two-block system. So we have the speed of the two-block system, which is Vs. And we're trying to find, so we need to get rid of the initial speed. Okay. So real quick, so we're kind of breaking it into two different parts. So from here to here, we're worrying about energy. From here to where they collide, we're going to be talking about momentum. So this final velocity here, even though we're treating it as final velocity, is actually, so we're calling this final velocity x, final velocity x, final velocity x, final velocity x. But our final velocity x is the same thing as our initial velocity for our momentum, because the energy it stops changing right at the end and it goes into our momentum. So that's how that works. So we can just plug this into there. And so we get our mass x, which is the square root 2GHX divided by mx plus my equals what we're looking for. So that's how we get there. So the biggest thing to get from there is to know that when you're on the ramp, you're dealing with energy. When you're on the flat surface, you're dealing with momentum. So that was the big catch on that one. Okay, so part B says design an experiment procedure that students could use to graphically determine the relationship between the released height of blocks X and the speed at which the two-block system travels after the blocks collide and stick together. So we're going to be using this equation we just derived from. In the table below, list the quantities and associated symbols that would be measured in your experiment and the equipment used to measure them. Also, list the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you may add them. Okay, so basically we're just listing the equipment that you would need. But then it says describe the overall procedure to be used, referring to the table, provide enough detail so that other students could replicate. So again, this is just like any lab I've made you do. You listing your procedure. You can do it in paragraph form or you can do it in step-by-step. I personally would do it step-by-step just so you don't miss anything and it stays very detailed. So step-by-step, you said you would, so an example would be use an electric balance to measure the mass of block X and block Y. So you need to know the masses of the blocks. Place block Y on the horizontal surface in the small distance in front of the bottom of the ramp so that block X horizontally collides with block Y. Place a motion detector in front of block Y so that the two-block system will travel towards the motion detector immediately after the collision. You don't have to use a motion detector. You could just like put it to motion detector measures velocity, displacement, stuff like that, time. But you could have a timer, you could have a meter stick there and everything. It says use a meter stick to measure the vertical release height of the center of mass of the block X when placed on the ramp. Activate the motion detector and release block X from rest. Stop collecting data when the motion detector of the two-block system travels to the motion detector. Repeat the experiment for several trials for the released height. From the released height. Repeat steps 1 through 8 for different released heights. So a couple of things you would need to measure mass. So in your little box here, you would have quantities to be measured would be mass, represented by an M, and that would be an electric balance. You're measuring for the velocity would be your motion detector. Height would be your meter stick. But instead of motion detector, you could do timer and another meter stick. So there's different ways you could do for this one. As long as it makes sense, they'll accept it. So for part C gives you a whole different setup. So part C is a whole different setup. We have a ramp. Looks very similar to what we had before, but now we have block W with mass M, and we have block Z with mass M. And this is the initial. And then again, we have the, same setup. But now it's saying that block W hits block Z, and then block Z goes moving. And it gives you a data table. So it states, students repeat the experiment, but replacing block X and block Y with block W and block Z, as shown in figure 3. Block W and block Z have identical masses. M. When the experiment is conducted, the students observe that the blocks do not stick together, as shown in figure 4. The students predict the speed of block Z after the collision by assuming that the collision is a perfect elastic. So remember, perfect elastic means they bounce off. They then collect data about the actual speed for both blocks immediately after the collision, as shown in the table. Why does the prediction speed of block Z after the collision not agree with the actual speed of block Z after the collision? So they predicted that the speeds should be the same. If the exact same mass, they should be the same. And so the predicted, the predicted, like for the first one was 1.75, and the actual was 1.32. So it's a little off. They're close, but they're a little off. So it's asking, okay, so why? Why are they a little off? And basically it's because it's not a perfect elastic collision. So the two blocks don't remain stuck together during the collision. The two blocks maybe they stuck together. So if they even stuck together a little bit, there's a loss of energy. Since there's a loss of energy, the speeds wouldn't be exactly the same. In a perfect world situation, they would be perfectly elastic. That's where perfect. But in most cases, in real world examples, like a lab, a situation like this, there wouldn't be perfect elastic. So it's a good assumption. They can assume that, but their data didn't give you that. Just like if you do the lab, the data wouldn't give you this. And it's because there's probably some little bit of stickage. There's some loss of energy somehow. Okie dokie. So number 2. So number 2, this says this question is a short free response question. Show your work for each part of the equation. There's another little diagram. It has a ball that goes, hits, and then it hits. It has arrow. It says theta. And the thetas are the same. Pretend like they're at the same height. I think that it is. It just, this ball's not as big. It's probably what's throwing. There we go. And it's telling you that up is positive and to the right is positive. That's what that little thing right there is telling you. It goes to explain. The ball is thrown towards the ground. The figure shows the direction of the ball before it reaches the ground and the direction of the ball after it bounces off the ground. After the bounce, the ball leaves the ground with the same speed that it had before the bounce. The angle between the ground and the ball's direction of travel is theta naught, before and after the ball bounces off the ground. The positive directions are indicated in the figure. A. Each grid below represents a component of the change in momentum of the ball as a result of the bounce. On the grid, draw a vector arrow that indicates the direction and relative magnitude of the change in momentum of the ball as a result of the bounce. If there's no change in the momentum for a given component, write no change under the grid. So so basically this is momentum, but they're breaking it into 2D. So you have to think about the x direction and the y direction. So anything in 2D, you can refer back to projectiles. So in projectiles, we always had a change in y, but we had no change in x. So it'll be the exact same thing. So for your horizontal component, there's going to be no change because there's no force acting on it. Your change in y, there is going to be a change because there is gravity. It's going to speed up and then slow down. So anytime there's a change of velocity, you have a change in momentum. So your momentum in the x will stay the same. Your momentum in the y will not due to gravity. And your component, so if you did like the little grid, for the y, your component would be, there's a change going up after it hits. So it's going up. And the reason it's going back up, that change is it hitting the ground. There's a change of momentum because there's a change in direction. Anytime there's a change in direction, the change in direction is up. It's still moving to the right. So there's no change in x, but there's a change in y because it's going down, it's going back up. Part B. It says, on a ball of mass m, and there's a little diagram. Let me draw a little diagram. So we have a ball. It's saying that it's at height h1. We have another little diagram that's saying it had h2. This is before, and this is after it hits the ground. So a ball of mass m is released from rest at height h1 above the ground. After the ball reaches the ground, it bounces and travels to height h2 above the ground, as shown in the figure. In a clear, coherent, paragraph-length response, this is one of those you have to write a paragraph for, that may also include equations and drawings, explain, using the conservation of momentum and conservation of energy, why your h2 is less than your h1. So this is where you get you start pulling in your conservation of your change in gravity and your change in energy, and how your conservation of momentum isn't conserved in the system because the wall is exerting an outside force. So one of the examples is the gravitational potential energy of the ball Earth system, and that's, you have to tell what system you're dealing with too, is converted into kinetic energy immediately before the ball reaches the ground. During the bounce, mechanical energy of the ball is converted into a non-mechanical forms of energy. Basically, you're not considering the ground in the system. So it is the ball Earth system, not the ball ground Earth system. The Earth and ground are two different things. Earth makes gravity. The ground produces a force going back up. So that ground would be an external force. That's why it's a non-mechanical form of energy, which decreases the kinetic energy of the ball after the bounce occurs. This means that the collision is inelastic. and the total momentum of the ball decreases since some of the momentum was transferred to the ground. With less kinetic energy, there is not enough mechanical energy to convert its gravitational potential to the ball Earth system to reach height 1. So that's one way you can say it. So yeah, and so just using, there's external force, using those keywords, external forces, Earth ball system, potential energy, kinetic energy, loss of energy, conservate, using all those buzzwords, you got it. And that is it for Unit 5. If you have any questions, please let me know. Remember, you're loved and appreciated. Bye.